All right. Can you guys hear me okay? Just to make sure before I start talking a lot. Can you type in the chat if you can hear me?
I can hear
Oh,
you.
okay, perfect.
I'm watching my daughter though, so I'm gonna put you on mute. I'm gonna mute myself, but I don't
Totally
even know
fine.
how it's
Yep.
gonna work out. She's only 2 years old, so I don't know how to work
Oh,
out. I might get out of here, but we'll see.
yep. Sounds good. Well, either way,
Thanks.
it's recorded. So, okay. So yeah, I will get started. Share my screen. I just wanted to touch base on the course here. Just we're halfway through, so I wanted to save some time to talk about that. So we are on week 4 now. So looking at week 4, this is what you should have done at the end of this week. So, and again, there's no due dates for this course. So if you're a little behind, that's okay, but definitely don't get too far behind. But for this week, we have electrical quiz 5, electrical quiz 6, and control logic is the amateur module. Week 4 math is here, and it goes into a lot of fractions and how to simplify fractions, which I will say that the components that you talk about in week 4 are really helpful for week 3. Like we talked about parallel circuits last week and that kind of confusing math equation that had a lot of fractions in it. So then if that confused you at all, the week 4 math might be beneficial. But all in all, for the electrical side this week, I think that the content is pretty straightforward. This is probably one of, not the easiest week, but maybe one of it's more on the easier side than some of the weeks to come. So just to kind of foreshadow here, we have week 5, week 6, and week 7 after this. So we're pretty close to being done. So this week, what it's primarily over for electrical quiz 5 is going to relate solely to these 3 lectures. So, and I'll talk about it today and some of the main components that you should take away from this these 3 lectures. But these 3 lectures, all quiz 5 is all about that. Quiz 6 goes into batteries. So this first video talks about batteries from like a broader sense. Basically, why are they useful? Why are they beneficial to modern day electricity? And, that's sort of just so I guess the components of a battery. And then lecture 25 and 26 kind of go into batteries wired in series versus batteries wired in parallel. What's the difference? How do you calculate total voltage? Ideas that we've talked about in previous weeks, but now we're just talking about batteries. So electrical quiz 6 relates solely to batteries. And there really are not a lot of calculations this week. So if you don't like the math side of things, that should be a good thing. But so coming up, I brought this up a couple times, I know, but week 5 is the hardest. Week 6 is also hard. And I think week 7 is not too bad. So week 5 and 6, so next week and the following week are easily the hardest weeks of the class. I've shown this diagram a couple times, but hoping if I showed enough times that eventually you'll become familiar with it for next week. But this is the diagram. So the quiz for next week is based solely off this diagram and this diagram. So next week, basically, I'm going to, and all in all, the quiz questions for next week, and I know I'm foreshadowing a little bit, but just in case you're getting ahead, the quiz for next week. So when you open the quiz and look at the quiz questions, it's going to say things like, what is the current at this branch, or what is, so basically you have to kind of solve different components of this circuit. And next week in class, I will probably just go through both of these examples and kind of help solve them for you. I won't give you the answers to the quiz, but at least I'll help you solve the circuit. So that part makes it a little bit easier. So just a heads up that next week can get really challenging. So reach out if you have any questions or concerns. And the videos are really helpful. So if you're going to watch any videos for this course or pay attention to anything, it's lectures 28 through 31. next week. Those are really important. So definitely, you'll notice that the examples that are done in these, I think lecture 4 and lecture 2 or 29 and 31, the examples that are done basically look exactly like these two situations with different numbers. So definitely take a look at that. But okay, so back to week 4, since that's what we're on. And electrical quiz 5 and electrical quiz 6 should be done. And the control logic amateur module. But okay, so before I get started on the PowerPoint, just want to like check in any questions or concerns with, like I said, at large, anything right now or next week or this week. I don't hear any. Okay, not hearing anything, so I'll take that as a no, and we can get started with this week. Okay, so the main ideas from week 4 and kind of going back to what it shows in the video, types of switches, relays, relay ladder logic. The main idea that's brought up is this idea of NO, NC, closed and open. So basically what NO means is normally open. So if you ever see that acronym, which you will on the quiz, it just means normally open, which I'll talk about in a minute, what that means. And then NC is normally closed. So I'll talk again about what that means in a minute here. First, I want to touch base again on parallel versus series because it's important for the topics for this week. So, and also the idea of a switch is important. So if you remember in the first week of this class or so, we talked about what a switch was and how basically when a switch is open, it means that the electrons, or electricity can't flow through the whole circuit. It's going to reach this point right here, and it's not going to be able to get through because there isn't a complete path for the electrons to flow, which means that our light bulbs or whatever we have in the pathway as our loads is not going to light. So this idea of a switch is really important for this week, and it's really the main, at least for besides the battery portion of this week, that's the main concept that we are introduced to. So again, just a picture at large. So electrons are going to flow all the way here, they're going to get here, and then since the switch is an open switch, so it's open, our electrons aren't going to be able to go through, and so they're never going to hit this load, and it's never going to do a complete loop, so electricity is not going to flow. So that's a big thing. When a switch is open, electricity does not flow. And that's important for when we're talking about normally open versus normally closed. I think that this diagram on the right is the most helpful for visually understanding what the difference is here, but also, it writes it in words. So when you're told that a limit switch is normally open, it means that in the normal state for that circuit, the electricity does not flow. So you have to energizing. So if you energize it and switch it on, it'll close the contact, causing it to allow current to flow. So what that means is that this right here, as it stands, is a normally open switch. And that is because at the normal state, it looks like this. And we would have to close that switch in order for electricity to flow. So when something is normally open, it means that we have to do something in order to close that switch and get electricity to flow. So an example of something like this would be a button that you have to hold in order for it to work. So if you don't press looks like a machine, like, just a typical machine at a, car factory or anything. If you have a machine where you're pressing if you don't press anything, it doesn't energize the robot, right? Or I'm just, again, I'm just putting an example out here. So if you don't press anything, it's not going to energize that robot. But as soon as you press that button, it closes the switch and allows that robot or whatever you need to energize to be energized. Then that's an example of something that is normally open. So in other words, a normally open circuit means that unless we press a button or do something, it's not going to energize. So these can be beneficial for a couple different reasons. So The biggest example of like why you would have a normally open situation is like, I guess I can give an example in the water industry. So for water industries, you have to, a lot of times they fluoridate the water. So they add fluorine to, help with dental issues and preventative tooth issues. And so they a lot of times will have a dead man switch, it's called, in order to fill a tank that feeds fluoride to the water. And the reason I'm talking about this is because they have a dead man switch, so they don't overfeed fluoride. So as soon as they press that button, it energizes the pumps to feed fluoride, but as soon as they let go, the fluoride stops. And the reason for this is because you have to press that button and you have to hold that button in order for the pumps to be energized. And that's important because we want it to do that, because if we just had it constantly running fluoride, then we'd overfeed fluoride. So again, open switches are normally open situations are important because it means that, we have to do something physically. So we have to press a button or lift a switch in order for that switch to close, thus electricity can flow. Does that make sense? I know that is kind of confusing, but in short, a normally open situation just means that electricity looks like this, it's not flowing, and we have to press something or do something to close it so electricity flows. But, and again, stop me if this doesn't make sense, but we'll do a couple more examples in a minute. But so this is perfectly on this left here is an example showing that normally open in the normal state looks like this. So we have that switch open and we have to hold it closed like this, and then electricity can flow. So normally closed situation is the exact opposite. Basically, it means that at its normal or contact state, it looks like this. So it's basically the opposite of a normally closed. So it doesn't look like this. It looks like something like this picture here. So there's wherever the switch is on this right side here, it's closed, right? It's a complete path. So for a normally closed situation, if we hold a button, it opens that switch and will stop energizing whatever you need to be energized. So an example of like something being normally closed would be like an emergency stop button. So if you have a machine where it's constantly running, then it's a normally closed, and this is simplifying things, but in real world, it's not this simple. But if you have a machine that is normally running, you don't have to do anything for it to run, and there's an emergency stop push button. As soon as you push that button, if the machine instantly turns off, that would be normally closed, because it would mean that at its normal state, that switch is closed, so electricity is flowing, it's being energized. And when we press that button, that switch opens, and so electricity can no longer flow. So I think it's kind of confusing. And the reason that this week kind of trips people up sometimes is because when you have a normally open situation, it means that electricity isn't flowing when you have unless you do something. Whereas if you have a normally closed situation, it means that electricity is flowing until you tell it to stop. So closed, I guess, essentially means flowing, and open means that it's not flowing. It was just kind of like opposite to what you would think. If you heard open, you think it's on, but really it's kind of the opposite. But if you ever get confused, I think that this diagram helps a lot. Like remember, what normally open is at its primary state and what it is for normally closed. So for series circuits and parallel circuits, it's a little bit different when dealing with normally open versus normally closed situations. And that's just because in a series circuit, we only have one pathway, whereas in a parallel circuit, we have multiple pathways. So let's say that we're first going to talk about series circuits because it's a little more straightforward. And then the next slide in a couple slides, we'll talk about parallel circuits. Let's say in a series circuit, if there is a normally open switch, it means that power is not flowing in the circuit. So a normally open switch would look like this. So it's open like that. So we do not have power flowing through the circuit. And when that normally open circuit is closed, so when a button is pressed, that's when power starts to flow in the circuit. On the contrary, in a normally closed situation, when you press a button, it'll stop the flow. And that example on the bottom here is basically what we just talked about. So let's say you have a light that is constantly remaining on. So, you know, anywhere, right? You have a light that's constantly remaining on, and for it to be off, this means, or for this to be constantly on without you doing anything, this means that it's considered a normally closed situation because that light's on without us touching anything. And so that means that that circuit is constantly having electricity going through it. So if you push a button and that light turns off, that means that the circuit is open. So normally closed situations are basically the opposite. So it means that electricity is being powered and it only turns, you know, off, or, you know, this is a normally closed situation, which means that electricity is being powered and it only turns off when a button or some method of control, like pressing that button, is to open the circuit. So I'm going to pause again, but just to make sure, does the idea of like a normally open versus normally closed circuit, is that any, hopefully that's clear, but please interrupt me if it's not. And for now, as long as you understand series works like that, then that's half the battle. So. Okay, so this is an example of something that you will get on the quiz for this week, and one of the harder questions that you will get. The question on the quiz, I think, has this worded a little differently, so you have to be mindful of your wording, but I just wanted to do an example of something that you'll see on the quiz or a similar situation. So whatever the answer is here, I don't know if it's the answer on the quiz, so just be mindful of that. But okay, so let's say we have a simple robot that has the following control circuit. So an on-off power switch controlling the power to the robot and the controller, a dead man switch wired to an MC relay, and an E-stop push button tied to an NO relay on the teach pendant, which is used to manually move the robot. And the question is, how do you get the robot to work? So it's kind of like a puzzle, and I think it's kind of fun. So basically what I did here is I first highlighted the three situations we have. So you have to read the question carefully and figure out what you're dealing with. So said that we had an on-off power switch, which, you know, is pretty straightforward, a dead man switch, which means you have to hold it the whole time for it to work, and an E-stop push button. On a sidebar, something that I recently learned is that a dead man switch it's called a dead man switch for a reason. And the reason is because basically it means that if you have to hold it constantly for it to work. So if you died or someone, you know, passed out, obviously they would fall and no longer be pushing that button, so it would stop working. So it requires a live human to push the button. So that is why it's called that. But yeah, so basically the three situations here you want to work through. So the first one's pretty straightforward. If we have an on-off power switch, we know the power must be on in order to operate the robot. The second situation here, a dead man switch, and it says in the description that it's normally closed. So if it's normally closed, that means that electricity is flowing, or if we go back to this, if it's normally closed, it means that electricity is flowing without us doing anything. So we don't want to touch that button, right? Because if we touch that button, it's gonna make it open like this. So that means that we're not going to do anything. So that's why in this example, it says pressing a button will open the circuit. So we're not going to do that. And then third, that E-stop push button is tied to a normally open relay on the teach button. So in this example, since it's normally open, going back to here, it means it looks like this, which means we have to press that button in order to close it and energize the circuit. So that would mean that we would want to press that E-stop push button, which is, you know, no, this isn't really a real situation because obviously an E-stop button normally when
It was kind of backwards.
yeah, it was a little backwards, but yeah, so I guess put a different word there, but if that helps. But at the end of the day, the main thing here is just knowing NO and NC and knowing if that means you should push the button or not push it. That's really as straightforward as it gets. And you're gonna have situations like this, and hopefully the ones with the quiz would have this be NC, because that would make the most sense. But yeah, so that's an exact example of one you'd see on the quiz. Like it'd have you go through 3 different situations, all relating to the same thing. Okay, So now this is where it gets a little difficult. And so basically this example that we just did was a series circuit because, well, it didn't tell if it was a series circuit, but it should tell you. If it doesn't tell you it's a series circuit, you should be able to assume. But in parallel circuits, as I mentioned earlier, since there are multiple pathways for electrons to go, it gets a little challenging because if one pathway has an open circuit, the electrons would still flow through another path that has a closed circuit, which means that this idea of normally open and normally closed isn't always going to mean that this circuit instantly shuts off. And if you remember, like one of the first weeks we talked about Christmas lights and how in parallel, you can tell if it's a parallel string of Christmas lights because if one goes off and the rest of them stay on, it means that one break in the circuit didn't cause the whole entire load to go out. So that's kind of the same idea here. So in parallel, if you have a switch that's open somewhere, it doesn't mean that electricity can't flow in other places. So in the bottom there, I'm just going to read that. So if you have a circuit with two switches in parallel, so again, parallel is when it looks like this example here. So you have a switch maybe on this branch and you have a switch on this branch. So if you have a circuit with two switches in parallel that is normally closed, which means that flow through the circuit is started without doing anything, and you open one switch and not the other, there's not going to be a change in flow. So it might stop, in one path, but because it's parallel, we will have another flow for electrons to go. So that's another thing that I think is on the quiz and that it might ask you. Like, I think it actually asks you exactly that. So, if you have multiple switches and they're all normally closed and you open one, that is electricity flow. And if it says parallel, the answer is no, because we have, other pathways for electrons to flow. So this is another type of example you might see for this week. So in this example here, let's say you have 4 push buttons in parallel with only one light bulb at the end. How can the light bulb light? So the answer here is that you would only need one button press. And so this is because in normally open, and this was assuming that these push buttons were normally open. So normally open, all of our circuits are open, but we have multiple pathways in parallel. So we really only need one pathway to be closed to light the light bulb. So, it doesn't matter how many push buttons you have in a, parallel situation. If we just have one pathway, that's all that matters. And so another example that's kind of interesting to kind of think about this in reverse is if you have a machine that you have to press 3 buttons at once for the machines to work, we know this is series. And the reason we know that is because, like we just talked about, if this was parallel, if we, just close one button or press one button and close that switch, we'd have a pathway for electrons to flow. So in a situation where we have to press all 3 buttons at once, we know that it's series because we have to close every single pathway or every single switch because we only have one pathway. But okay, so that was basically the main ideas from the first half. So really to kind of summarize what you should have gotten out of and going back to like how it relates to these lecture videos, these 3 lecture videos in Electrical Quiz 5, that's really what it relates to. So I wonder if I can I don't think it'll let me take the quiz, but nonetheless, the quiz questions are going to relate to, they're going to give you parallel situations, or this quiz 5 is what I'm talking about. This quiz 5 is going to give you parallel situations and series situations and ask you to evaluate, depending on if it's a normally open or normally closed situation, how do you get electricity to flow or how do you get electricity to stop? And that's really what that quiz is about. So the next section or segment of this week 4 is talking about batteries, which I would say the second half here is definitely probably the easier half. Some of the questions are kind of straightforward, like why is a battery useful? But some of them it can be a little bit challenging, so we'll talk about that a bit. But I did want to play a quick video. So if you saw, I sent a video today in my email, which I had it up here. So hopefully you can let me know if you can't hear the audio on this. Hopefully you can, but I don't know. I always like short videos like this. They always help me, but. So it's only 4 minutes. So if it doesn't help, then it's only 4 minutes. So. Okay, just make sure can you hear it?
No,
Dang it.
I mean, I can slightly hear it, but no, not really.
I wonder if there's well, that will be frustrating. One sec, I'm gonna see if there's like a way to,
It sounds like it's in the background. But I mean.
yeah,
for
I feel like
a
on
little bit, I did
Zoom,
hear.
okay, give me a minute. I feel like on Zoom, there might be like a way to. Select the speaker.
I don't know if it was just me. I don't know if the other guys could hear it.
No, it's probably the same. Press and hold, show. Thanks for being honest. Most people, when I say yeah, they just say, yeah, we can hear it. But they probably can't, so I normally
I'm trying
probably
to
play an 8-minute video without. Okay,
I turned mine up all the way just so I could hear it, but you already turned it off.
okay, well,
Yeah, it was quick.
all right, maybe I didn't play it long enough from here. I'm gonna just, okay, I'm gonna just try it again and we'll see.
Your phone utters its final to and cuts out. In that moment, it feels more like a battery almost.
It's not smooth.
No, it's choppy.
It's choppy. Okay,
It's
dang
super
it.
choppy.
Well, it's only 4 minutes.
I
Well,
did
either way,
get it.
I mean, we can watch it.
Yeah,
I
it's
did
not a
get it
big
in
deal.
my
I'm
email.
not gonna make you watch the whole video, but I wonder if I can zoom to the parts that are relevant. But I would definitely recommend watching this. It basically just talks about why a battery works the way it does and why it's a critical component to circuits, which, you know what, actually, I'm just gonna pause and show this. So basically what they're showing here is the two sides of the battery. So we know that we have a positive side and a negative side. And then, like we've talked about this whole time, we know that electrons are flowing. Something we haven't ever talked about is the fact that electrons flow from the negative side to the positive side. So anytime that we have a circuit and we have a battery here, they're flowing this way, negative to positive end. So that was one thing I wanted to touch on, but this video basically just explains why electricity flows like that, which is really the whole point of a circuit, right? So like the electrons want to get to the negative side to the positive side. And that's essentially, if you keep going here, it shows that like this is what creates a circuit. Is that, desire, I guess, to go from the negative end to the positive end. And it talks about it from like a chemistry standpoint on why that works and why that's important. So I won't play it, but just, yeah, I think it's interesting. So, okay. So, okay, going back to this. I'm not going to touch too much on like a battery I'm not going to touch too much on the content that's gone over in this one. So definitely watch this lecture if you still have questions. But then that one just goes over batteries from like a broad sense. But basically, battery is just a portable power source consisting of one or more electrochemical cells with external connections for powering electrical devices. So the external connections, are the tops there. And, they're useful because they carry electric charge for long periods of times and can be reusable. So in this picture here, which I can put it in view so it's a little bit easier to see. But in this picture here, like that video just showed, electrons move from the negative side to the positive side. So that's what these arrows are showing, just so we're going from negative to positive. But there's also 3 components of a battery: cathode, the electrolyte, which is the middle, and the anode. So the anode is considered the negative side, the cathode is considered the positive side, the electrolyte is somewhere neutral. And if you've ever taken a chemistry class and you learn about ions, which are basically just, charged atoms, something called a cation is when it has a positive charge. Something called an anion is when it has a negative charge. So that's kind of where these terms come from: cathode, ion, anode, anion. So that's how I always remember it. So if you ever taken chemistry class and dealt with ions, hopefully that helps. But basically that's the main idea here is that batteries flow from negative to positive, and that they're stored when electrons are separate in the battery, they're stored on the anode side, which makes sense because we know they flow from the anode to the cathode side. So I think that's a quiz question, just a heads up. So it asks where batteries are stored, and the answer is the anode. Again, that's where it starts, and that's where electricity flows. And then really, honestly, the main thing that's brought up are the difference between parallel and series and calculating total voltage. So batteries in a parallel circuit always have the same voltage. And the reason for that is because going back to right at the beginning here, if we have a battery, anywhere, we need the same amount of voltage in every single pathway, which means that wherever we have batteries, we need complete energy because every single loop has to have enough voltage that we need. Whereas in a series circuit, we only have one pathway. So that's important to remember. So again, in series circuits, our voltage, if we have multiple batteries wired in series, the total voltage is going to be different, or the voltage of those batteries is going to be different. And I'll talk about in a minute how you would calculate that. And then in parallel, those voltages are always the same. So to kind of talk about, so we don't really have to talk about situations in parallel because again, it's straightforward. If you have two batteries that are wired in parallel, they have the same volts. So if one's 10 volts, the other one's 10 volts, it means the total voltage is 10. Batteries in a series, on the other hand, you do have to do some math, but it's pretty straightforward. And basically the thing is, if you have, depending on, normally I think in this class, you're only going to be dealing with two batteries wired in series. So for example, if you have a 10 volt battery and a 3 volt battery, and they're wired in series, the way that we would determine what the total voltage is we would want to look at the way those two batteries are connected. So in the quizzes, they denote it like this, which basically is saying that we have both positive sides of the battery touching. So like if you picture like one of those light bulbs where you have to like stick all the batteries in, you wouldn't ever do it like that, or like a remote, anything, right? Like you wouldn't ever do it like that where you have the positive ends touching, but that's basically what that's insinuating when you see that. And then the situation is what we're used to, which is when we have, the opposite ends touching. So basically when you have for series circuits and your batteries are wired in series, the way that you would calculate what your total voltage is going to depend on what situation you have. If the two like sides are touching, you're going to subtract the largest voltage from the smallest voltage, and that's your answer. So in this situation, since we had a 10 volt and a 3 volt and they're touching, 10 minus 3 is 7 volts. However, if we reversed it and we had those positive and negative ends touching on that 7 volt or on that 10 volt and 3 volt battery, we would add them together. So it would be 13 volts. So basically what this is showing you is that and in real world situations, we always have it like this. So we always are adding the voltage together. But you can, for mathematical sense and for like fundamental knowledge, you can, if you put them positive, you're going to subtract, which it kind of makes sense. Like if you think about it, like that's why it doesn't work if we do put batteries in wrong, and it's because we're not getting the amount of voltage that we need. And I think that's something, so I wrote it here just as like a remembering point. So when your same poles are touching, you subtract. When your opposite poles are touching, you add. And it also helps because opposites attract. They always say that with like magnets and stuff. So that always helps. Like opposites attract, so you add. But I did find it interesting. So in the videos, Eddie talks a little bit about like, and a lot of people ask sometimes, so are there any benefits to having a situation like this where you would have the positive ends touching? Like, let's say you wanted a lower voltage on something, would we intentionally design a circuit to have the batteries be wired like that? And the answer is no. So And the reason for that is because it's essentially just a waste of battery. There's easier ways to lower the voltage than wiring the batteries differently. So the easiest way to lower voltage is by just adding more resistors, which, if you think about it, makes sense because going back to what Ohm's law is, I'm gonna write it here. That's really small, so actually let's write it on the next page. So Ohm's law equals V equals I times R. And anytime, one thing we talked about at the beginning was if you increase or decrease your resistance, it's gonna automatically increase or decrease your voltage. So let's say, for example, we wanted to calculate voltage and we had a current of 5 and a resistance of 10. So current 5, resistance 10, it would mean we had a voltage of 50. If we decrease that resistance, to 5, be 25 volts. So they're related. So basically, the just main idea here is that the easiest way to resistance and voltage and current are all related. So, if we're designing a circuit, we'd never design the batteries like that. We would just easily manipulate the resistances to do that. But yeah, so basically those are the main ideas from the second half. So some of the questions I think we'll ask you questions like this. So as long as you know how to either add or subtract, depending on how your batteries are wired in series, you should be good to go. And then just know, that batteries and a voltage are the same in parallel. This design for what the battery looks like, and then just a little bit about batteries from like a qualitative sense. So there's not a lot of math in that second or in either of the 2 quizzes from this week, but and some of them you could probably answer with prior knowledge, especially some of the battery questions. But yeah, so really that's the main idea from this week. So just
I got a question.
Yeah.
Now, this week 4, I got your slides in the email. The previous weeks, I have, it said that it was attached, but it was not. I just actually went while you were speaking, looking to see if I could find them.
Oh, well, that's
Yeah, which, these slides really help because I can print them out, I can use them as notes.
Yeah.
But I haven't been getting them, so I was curious if you could possibly email me the previous slides.
Absolutely. Yeah, I'm so sorry. If I would have known sooner, I would have fixed that sooner. So I totally apologize. Let me see.
Which that's why I emailed you about taking the quizzes. I took the quiz and then I was like, I don't want to do it again until I've got everything at my.
Absolutely. Yeah. You know what I'll do is I will post them in Canvas, and I will do that right now. So that way, if for some reason it's not opening through email.
Like I've gotten your YouTube videos, the link.
The link, okay.
The attached slide. Now today the slides were there. I downloaded them, I put them into my computer. But the previous ones that I went through every one of our emails together and it was not in there, so.
Okay, I normally send them out in a mass email. So I sent today's on Thursday, but I
Right, which I got the email, said, week 3, here's the slides or whatever, and it's nothing was
There.
attached. Yeah.
Does it show the attachment and it just won't
Nope.
open, or it doesn't show it?
Nope, nothing.
Huh.
Which today it did. I don't know if anybody else is having that issue with that.
Yeah, do you want the old ones?
I
'Cause
haven't had any issues at all, but I haven't looked, I didn't look at today's, but I haven't, I know.
Have you been getting the slides?
I didn't check last week's either, because I just got some free time today.
I'll send, I'll make sure and let me know next week if the week 5
Okay.
don't send beforehand. I'll send them early, so I'll send them on Monday. That way, if Cause I sent these ones on today, so if they didn't work today, I wouldn't have been able to even get it in time, so I'll send them on Monday and let me know prior to Thursday if they still don't show. I'll try to send it as a PowerPoint and a PDF, and then hopefully one of them will show up. And
Or
in
if
the
you could send-
meantime,
If you can send the last ones, because I'd like to, ta-
absolutely,
take the quiz over again.
yeah, yep,
There's two quizzes, I think, but. Yeah, I just
So
didn't want to do that without all, everything at my fingertips.
yeah, week 3 is pretty important. You know what, I'll just do it, I'm gonna send it right now, that way you can open them and then,
Okay, thank you.
yeah, of course. I think this is your email, I'm hoping.
Yeah, because it doesn't tell us which ones we got wrong, which is,
I know,
it's like, that's the kind of like, how do we fix if we don't know? Like, my thought process is like, if we were writing these down on paper and we handed it in, we're gonna get a red mark on next to the problems that we got wrong. Then we can look at it and go, oh, okay, now we know. And then we don't really need to know the answer, we just need to know which ones we've done wrong. Otherwise, we think everything that we've done is wrong.
right, well, for one, I don't know if I have I don't think I can change it for the electrical quizzes, but I think the
Right.
idea was that, I don't think they always gave 2 attempts. And really, I think the only reason they gave 2 attempts was sometimes,
Well, I understand the attempts, it's just, we should know which ones we've done wrong. That,
right. I will say after your second attempt, for just like beneficial reasons, if you want to know what you got wrong, I absolutely reach out and I can let you know exactly what problems you got wrong. That's no problem. As for between your first and your second attempt, I can't tell you, but I can tell you like the concepts you got wrong. But and the reason for that is I just want to be consistent with, like, there's other sections of this course, so I know the other sections are set up like this too, that they don't tell you what questions you got wrong, they just tell you how many you got wrong. And that was just because, if there's only 8 questions and they tell you exactly what 2 you got wrong, just by basic statistics, you can almost go back and get the answer right. And I 1 in 3 shot. But, and that was, but I get what you're saying.
I guess, but at the same time, it helps us to focus on where we went wrong. Maybe.
Yeah, I totally understand. Like I said, if you don't know, if you take a quiz and don't know where you went wrong, send me an email and I can let you know what
Right,
conceptually what.
well, that's why I think having these slides is gonna help me a little bit more too, because.
Absolutely, yep, and I just sent that email, so you should have week 1, week 2, and week 3. So you're gonna open it, and if you can't open it, let me know. I'll try to send them a different way.
Yeah, I'm looking right now, I'll see if I.
Awesome, and yeah, I'd say week 3 is definitely one of the most hopeful ones, so definitely relook at that one. Okay, but I don't have any other topics or anything. That was this week. Next week will probably definitely take up the whole time just because.
Yep, there they are. Perfect.
Oh, perfect. Okay.
Hey, can I ask you something?
Of course, yeah.
When you say that, week 5 and week 6 are difficult, but
Mhm.
what exactly do you think, what's so difficult about week 5 and 6? I mean, is it just that there's so much more to it, or is it because it's more difficult,
That's a good.
mathematics, or what is it exactly?
So the reason week 5 is so difficult is because there's a lot of math. But, and I'll just foreshadow it and hopefully be able to show you the questions. So you're given this diagram, which, and in the videos we'll talk about, how like, especially not this week, but last week and the week before, we did a lot of like solving circuits. And we had to, in order to find the answer that we were looking for, we had to like backtrack and find do like, use like 3 different equations and calculate
Yeah.
one value in order to calculate, something
Oh,
else.
yeah,
the
it threw
voltage.
me right off because I
Mhm.
was going backward instead of forward, and I was going back to the week before to do the math again, and it was like I almost forgot how to do it again, so I luckily
Exactly,
have
so
notes, and so I was able to do well, but I just, I get what you're saying,
mhm.
about that, so, and now it's gonna introduce us to what?
So now you have both series and parallel components. So before we were only dealing with the series circuit. So when we were doing all these calculations, we were knowing, okay, this equation is what you use when you have a series circuit, and this is what I do every single time. And then if you had a parallel circuit, you knew, okay, this is the steps I need to take for the parallel circuit. I do this every single time. Now we have both components in the circuit, so it requires you to objectively look at the series or objectively look at the circuit, like this, and then you have to almost solve a puzzle to determine. It's like a ton of iterative steps. So like the question, so this is what the circuit looks like. And the questions will say things like, oh gosh, sorry, all over the place. The questions for electrical 7. Wonder if I can preview questions, preview. We'll say which steps. Okay, so it says things like this. Look at figure 2. What is the total resistance for the circuit when all resistors are combined? So going back to what we just looked at. Find it in here. I'll have it open, so it's gonna take, so that's what, so it just gives you something broad like that, like what is the total resistance, or question 11 is gonna say, what is the voltage at R1? So you'd have to go, and I'd open up 2 tabs so you can have it both at the same time, but like you'd have to go look at your week 5 diagram. And just by looking at this, you can't tell what the total voltage is. And it's a lot of times hard to like conceptually figure out, well, like, how do I get the total voltage? Because it isn't as straightforward as doing one equation. It's doing 6 different steps in order to have all of the right parameters to calculate total voltage. And that's why it's challenging, because it's not just what is voltage when you're given current resistance. It's, you have to really understand fundamentally every single week and all of the equations we did in order to solve it. But that's why I think it's the hardest thing. So in short, it's because when it gives you questions on the quiz, it's not as simple as using one equation and using one formula. It's, you have to do multiple steps in order to even have the right values to find the answer. If that makes sense.
Okay,
But
okay, well, I'm gonna sign off. I'm gonna just do some studying now, so I'll, catch you guys next week.
okay, yep, and yeah, reach out, of course, if there's anything, if you end up taking this quiz or any of the quizzes and have questions, just send me an email if you can't meet or anything, or I can help you via email too.
Okay, thanks, Summer. Have a good night.
Thanks, you too.
See you, Dan.
See you, bud. Bye, Summer.
Bye, thanks.